Hello everyone, welcome back to the channel. If you saw my previous video, you know I walked through the entire AVL tree system I built in C++, including the standard AVL tree and 4 of the advanced variants, the threaded AVL, persistent AVL, the hybrid AVL, and the cache-friendly AVL. In that episode, we covered performance, the memory layouts, rotations, and how these different versions behave in real-world high-performing computing. Today will be the last video of the series, and this is the final installment, and I'm introducing 3 brand new advanced AVL variants that add powerful functionality used in actual systems like databases, compilers, and scheduling engines, and other analytic frameworks. So let me just get into the project right here. Okay, so these are all my files here. So I've created a new ordered statistic avl.h and .cpp files, persistent AVL, and I'm sorry, not those, lazy avl.h and .cpp, and interval avl .h and .cpp. So just to let you guys know, in the video I'll walk you guys through the ordered statistic AVL, which supports the rank key and select, and it is used in statistics like leaderboards and database indexing. Then I will go over the interval AVL tree, which stores intervals L and R and finds overlaps, and this is seen and used in CPU scheduling, medical booking systems, and geometry networking. And lastly, I'll go over the lazy propagation AVL, which helps apply range updates in order log n, and it's used in segment trees, analytics engines, and memory managers. So you'll see how all of these variants work and the differences between them, how I tested them, and how they fit into the full interactive menu-driven system that I've built and I'm continually working on. So let's run the program. And let me just move my camera so you guys could see the whole screen. So here is my main menu. As you can see, I have the AVL tree main menu, which is for regular AVL trees. So if I wanted to insert, delete, search, traverse the AVL tree, display the structure, and then everything right here, exit. And then I have the 7th option right here, which is the advanced AVL variants. So as you can see, the first 4 I already went over in the video before. So if you guys want to watch that, or if you want to watch just the regular AVL tree where I just used this main menu right here, that's in the first video I uploaded as well. So let's get into here. So we will start with the order statistic AVL right here. So it brings us to this menu. So let me tell you guys a little bit about this. So in this, every node stores its subtree size, and it supports the rank key, how many keys are smaller, and select k, which returns the value of whose rank is k. Like I said before, this is used in ranking systems like sports or gaming leaderboards and other databases asking to return like smaller values, or even in stock market order books and stuff like that. So let me get into it and insert a couple values here. So let's do 15, value 15. I'm just going to do a couple so you guys could see how it works. Then I'll do 10 feet 10. And then let's do one more here. 20, value of 20. So let's display the structure. And as you can see, it displays right here. And And now let's do the rank. So let's do 10. And as you can see, it gives me the rank of 0. Why it gives me that is because 10 is the smallest value I inserted. So it's actually working great right now. Let's try another one, which should be rank 1. So if I do rank again and I put the key, let's do 15, it gives me rank 1 now. So it's actually working perfect. And yeah, so everything's working perfectly, and the subtree sizes updated correctly, and both rank and select return accurate results. So now that that's working great, we could go back. Let's go back here and let's talk a little bit about the interval AVL tree, which is option 6. So let's talk about this a little bit. It's one of the most useful structures in scheduling and range-based systems. It supports insert, interval, delete, and query for all intervals that overlap with a given range. I mentioned this previously as well, but it's what it's used in. So it's used in booking systems. It could be used in medical appointment conflicts, networking ranges, CPU and GPU scheduling, or calendar systems. And how it works is basically each node stores a start and an end, and there could also be a max end, which is the highest endpoint in the subtree, which allows fast pruning during overlap queries. So let's test it out. So let's do start with 1 and with 3. Let's do a couple of these. So I'm going to insert like 5, 20, 10, and 15. And let's do 17 and 19. Okay. Okay, so now now that we have those inserted, now let's try to use this option 10 right here, the query overlap. So let's do that, and it'll ask you for a length. An L. So let's do 6, and then the next one's 7, and it'll show you where it overlaps. And yes, so that's the right answer right here. So 5 and 20 is where it actually overlaps, and that's exactly right, because only the interval 5 and 20 cover the ranges of 6 to 7. So that's working correctly. So yeah, so that's how the interval AVL works. So now let's go into our final section, which is the lazy propagation AVL. So let's get into this. So let me tell you a little bit about this. So this one is extremely powerful. It supports the range add, range assign, and range sum, and it is used in data analytics, segment tree-like operations, updating thousands of values in order log n, batch processing, and financial calculations. The tree can store subtree sum, lazy add, lazy assign, and has assign flag. So this allows updates to be delayed and pushed when they are needed. So let's test a couple of inserts. Let's insert some numbers here. So when you insert, it'll ask you to insert a key and a value. So let's do 10, 5, let's do 20, 10, and let's do 30 and 2. Okay, so now that these are added, let's do range add. So let's do 10, 30 plus 3. Let's see if this works. Or let's actually, here. So let's actually go with another example. So I'll insert 1 and 1, 2 and 2, 3, 3, 4 and 4, 5 and 5. Let's do a couple more. 6 and 6, and 7 and 7. So what we could do now is we could check the range sum. So let's say we want to click this right here. range sum right here, option 12, and it'll ask us for the number. So let's do 1 and 7, and it should give us 28. So yeah, so that's actually right. And so what happens is that two nodes had the lazy add applied. One node had lazy add already pushed, so the final sum looked like 8 plus 13 plus 7, which is equal to 28, and that's what we have, what we got. So that's why the new total is 28. So as you can see, that's how the lazy propagation AVL works. So that's pretty cool to see how all three of these are pretty different from each other. So yeah, these three advanced AVL trees, order, statistic, interval, and lazy propagation AVL, complete my AVL data structure system. So the application now includes standard AVL, threaded AVL, persistent AVL, hybrid AVL, cache-friendly AVL, order statistic AVL, interval AVL tree, and lazy propagation AVL. So they're all fully integrated into an interactive menu-driven system in C++, as you could just see, that I designed. And yeah, so if you've been following this series, thank you. And this project has been a huge learning experience for me in my data structures journey. And with these three final AVL variants, the system is complete. So yeah, thank you, and thank you for watching. Have a great day.